The other mass transfer term in the Van Deemter equation is for mass transfer in the stationary phase. And we call this term C sub S. Mass transfer term being term C, and for the stationary phase gives us the S. Now for the mass transfer in the stationary phase, this kind of stems from how the analyte interacts with the stationary phase. So in the affinity for the analyte in the stationary phase. So let's see what this looks like, okay? So let's say I have kind of my analyte. So this is kind of my band of analyte molecules, right? I'm just kind of drawing it like that. So we kind of can see the two edges of this analyte. Bam. So all the analytes are kind of in this area. And I have my stationary phase here and my mobile phase here. And when they're interacting, this is my bandwidth here, we'll call that. So as the analytes are interacting with the stationary phase, again, we're at equilibrium. So some of them are going in, some of the ones in the stationary phase are coming out, okay? Now, this is, again, in equilibrium where we have some percentage that are below and some percentage that are above. So some are in the stationary phase, some are in the mobile phase. And we've talked about how we can consider the affinity for each using a K constant to describe the affinity in that equilibrium. But what happens because it's an equilibrium is that at some point the mobile phase is going to start moving. Okay, so the mobile phase is still moving. So while we have this equilibrium going on, after the move of the mobile phase, a small period later, okay, what was in the stationary phase did not change, right? But now the mobile phase has moved down the column. We have analytes in that mobile phase. Okay, so after the move, now what do we have going on? Well, we still have analytes that are going to be in contact between the mobile phase and the stationary phase. And so after the move, what do we see? We see that we're still at an equilibrium where we have some stationary phase molecules or atoms that or molecules that are adhered to the stationary phase are going to move back into the mobile phase. There's an equilibrium there that's now been shifted because there's nothing in the mobile phase. So these are going to be, the equilibrium is going to be driven to push those back into the mobile phase now. And the leading edge of this is going to also want to be at equilibrium with the stationary phase moving into the stationary phase. Now, what does this mean in terms of band broadening, which is our ultimate goal here to understand? Well, here we had a bandwidth that was pretty narrow. But after we started moving along with the mobile phase, now we have analytes that are spread all the way from here to this far leading edge. So our bandwidth for where the analytes are in relative position to each other is wider. Okay, so we've got a wider spread of where the analytes might be. So when you're considering when these are going to leap from the column, the elution time is going to have more variability because we've had some spread in the bandwidth of where the analytes are located. So what does this mean in terms of some of the ways that we would write this, okay? So what does this mean? This means CS is directly proportional to our flow rate, right? And the reason for this is that if we are moving faster, okay, if this mobile phase moves faster and there is an even more, this is a faster flow rate, then we might get our mobile phase piece even completely misaligning here. Okay, so now our bandwidth is even wider with a faster flow rate. So we're directly proportional to flow rate. A faster flow rate is going to make our bandwidth broader and make this term lead to a really high or really wide distribution of analytes and a less efficient separation. So what other kind of quantities affect our separation here? Well, again, we have a function of retention factor. And this is not the same function that we see in the CM term, but it is also related to retention factor. Okay? And this retention factor this time is going to relate specifically to the affinity of the analyte for the stationary phase. So this, unlike the in the CM term, we're looking at the function of the retention factor as it relates to the stationary phase, not relating to the mobile phase. So they're different factors. The other thing that can play a role here is what we call the film thickness, df squared here. So this is film thickness. And what this essentially means is it's the thickness of the stationary phase. So in this case, if we have a really thick stationary phase, as analytes diffuse into the stationary phase, they kind of get lost. Okay, they get stuck in there. There's so much stationary phase that they cannot find their way back to the surface in order to move out of the stationary phase and into the mobile phase. So very thick film for the stationary phase is going to lead to this CS term being much higher, because they're just going to spend longer in the stationary phase, and they're going to miss out on the movement that comes from the mobile phase and spread our bandwidth out. Now, the other thing that it depends on is the diffusion rate in the stationary phase. Because again, if it's going to diffuse very slowly, it will spend a long time in the stationary phase and never make it out to the mobile phase until after the bandwidth has moved largely down the column. And so in this case, it will make the bandwidth much wider because most of your analytes have already moved. Conversely, if this diffusion rate is very fast, it gets in and out of the stationary phase really quick before the rest of the group has really moved on, and it's going to keep the CS term very low. So it's an inverse relationship between diffusion in the stationary phase and the overall effect that your CS term has on band broadening. So what's the overall message for this term? The faster you can get in and out of the stationary phase, whether that's having a nice thin film thickness or a fast diffusion in the stationary phase, is going to mean that you're going to get less less broadening, because fewer analytes are going to be left behind in the stationary phase as the mobile phase continues to move down the column.